back home. So I got my BTech degree here many years ago. I wouldn't want to reveal how long ago, but some time ago, and I'm back here, and I want to thank Mahesh and Anubhav for giving me this opportunity. I was supposed to have come here April 2020. And we all know what happened starting in March timeframe, and that visit could not happen. And for me, just a trip got canceled. For many people, their life itself changed because of the pandemic. Interestingly, June or July of 2020, I first thought that the pandemic will go away. It's just a news media's hype, but then I was proven dead wrong. It's a really nasty disease that spreads incredibly fast, and we know what happened. So when that became clear around June 2020, June, July, airborne spreading is a very serious thing, and that is a very much a fluid mechanics problem. How it spread from me to you to other people in an auditorium like this. So me and some fluid mechanicians in particular, Soldati, he's an expert, I'm sorry, Zaleski, he's an expert in how droplets form from jets. Soldati and myself are sort of our expertise is in how particles disperse in a turbulent flow, in this case, droplets. Ahmadi is, he specializes on inhaling aerosols, how they deposit on the lungs and so on and so forth. And I don't know if you all followed Lydia Baraiba. She is absolutely world's leading authority on fluid mechanics of diseases. She's at MIT. So we formed a team and we started looking at this problem. First thing we did was to sort of frame the problem as, hey, when you speak or cough or sneeze, what kind of aerosols stay up in the air? That was the question that we posed and we answered, and we wrote a position paper on that. But then I continued on, and then the next question comes, okay, these aerosols, these are virus-laden aerosols are emitted. How does it spread from, say, a person like me here on the podium to far corners? So that's the problem that we started working on. We got great, interesting results. One point I want to make is that for such analysis to be useful, it must be simple. If you give very long equations and very complicated things, nobody will use it. So in other words, our ultimate interest was to impact guidelines, science-based guidelines. How do we form? So the theme is do a complicated analysis, but get the answer to a very simple answer. Can we do that? That's the challenge. And I want to report where we are. We aren't there yet completely, but I want to tell you about our progress. So what kind of questions that we have? So if you have a classroom, how many students should we seat? What should be the distance? I mean, of course, it's popular that people say 2 meters, but that came out of 1950s research. Now, we have landed man on the moon, but we haven't had a reasonable fluid mechanical analysis of how diseases spread. So that was the sort of motivation, is that the tools are there. We just need to have a persistent analysis of this problem and build it into a simple theory that can impact decisions. Okay. It's not moving. It did something. Maybe I should just use the other. No, no, that's okay. I'll use. Okay, so there are other questions, say in a restaurant, we might want to know how many tables to set up, or what the AC configuration. So there are many questions, say, for example, in the case of a hospital, how many beds to a room, or one real question I was asked by a hospital in Gainesville is when they do intubing or out tubing, they put tube for COVID patients and they do cough, how long should we keep the operating room empty? So they leave the room and they just played Russian roulette and say, okay, 45 minutes, we will keep it empty. So after intubing, out tubing, everybody will get out for 45 minutes and they will come. But we should be able to do better than that. I mean, we fluid mechanicians need to do slightly better job to give them guidelines, because one operating room is not the same as the other. We have the tools. How do we attack? So that's the kind of question that we want to do. One thing I want to tell you is that much of our recent interest came from COVID, but it's not just COVID. I mean, we all know even before COVID, flu season comes, half the population gets sick, and you think of how much productivity is lost, and we just take it for granted. Okay, you're going to get sick, it's going to be sore throat. And one thing, ever since COVID started, I haven't had better health than before. I haven't even had a day of sore throat, not a headache. It's amazing that. So what that tells is that if you're very careful and avoid catching bugs, we can be way healthy. So the question is, I think it is coming. Just like people do air conditioning calculation, there will come a time people will design rooms to be, may not be pandemic free, but the risk of infection will be minimized. So that instead of billions of people getting flu every year, even if you reduce it to 500 million, you have won. Okay, you're one big time. So some of the things that I'm going to talk about is that how diseases spread is the kind of theme that we want to look at. So there are three modes of spreading, and you may have heard of this. This is pretty obvious. The first mode of spreading is when you talk, when you sometimes stand next to your old person, you can see their spit coming all over. And that's the direct mode of transmission. The second mode is that, you touch your nose and touch your doorknob. That's the fomite, which is residues that fall and you touch it. And you then touch your eyes or nose, then you get infected. We all know these things. But the real one, which is sort of like a most dangerous one, is airborne transmission, because it's not limited to a few feet or a few meters. It can be all the way across the room. And how do I know that? You can see that somebody making a filter coffee or roasting masala, you can smell it halfway across the building. Your neighbor cooks something wonderful. We smell it. How does it come? So that's a clear proof that airborne particles do travel. The viruses are special that way because they're nanometers in size, and therefore they can travel very easily, whereas bacterium, not so easily. So they are mainly waterborne diseases. So airborne diseases is very hard to contain, especially disease like COVID, because it's excellent at spreading. Okay. Now, there are many documented evidences, and people have written papers on it. This Skagit Valley is how it spread there, or the Starbucks in Seoul, or bus journey in. There have been papers written on it, and there are very clear evidences that one sick person in the bus or one sick person in the Starbucks spread to not one, not 10, sometimes dozens of people. Now, one thing I stuck in here, during that time, I also read that there was some interesting story about somebody in Chennai, a single elevator spreading. I don't know how much is true and whether it has been studied or not. So I threw in there because of where the talk is. But clearly, and I had to warn my relatives that don't go into elevators because that's a great place for somebody if they have entered and they have sneezed, and you can easily get the airborne disease in just like that and get sick. So there is a clear evidence that these super spreading events all happen because of airborne spreading. Now, how do scientists analyze infectious diseases, how they spread? So there are a few metrics they use, and I want to sort of build from, say, infectious diseases to, say, fluid mechanicians' interests. So I want to go through the list of 3 items. The one thing that they look at is what is called the indoor reproductive number. That's a very simple number. If one sick person walks into this room, having 50 people, and you also have to specify the time in 1 hour, half hour, etc. What is the probability that another person will get infected? So if that number is 1, that means over that time, 1 more person will get infected. Now you can see it grows exponentially. So 1 person walks in, and in an hour, another person gets infected. That second person can infect 2 more, and then it sort of multiplies and grows exponentially. So the lower the indoor reproductive number, the better it is, because then the disease will just not spread very fast. But COVID-19 had a very high reproductive number, at least some of the variants, and therefore it spread very rapidly. So where does this come from? So we can dig in a little deeper, and we can look at what is called cumulative exposure time. So in other words, these are very related concepts. So from the reproductive number, we can, so if you want to set guidelines, you need to look at this, what is called cumulative exposure time. So again, what this is a product of how many people are in a room and how much time. Okay, so you can say, for example, in this room, if a sick person walks in, 50 people in this room, and you can specify the time, 1 hour, 2 hour, 3 hour, or 45 minutes, whatever you have it. And then you have to say a risk tolerance, and you can say, I want only 10% risk. So for a old people's nursing home, you would want the risk tolerance to be very high, because if they get sick, they're going to die. So in a kindergarten, maybe it's very low. So once you set the threshold, you can come up with how many people can stay in a room and how long can be exposed. Lower the number of people, higher the time. Larger the number of people, lower the time. So the product is the one that you want to control. So this is another number I want you to keep in mind. Now, ultimately, where do you get this thing from? You get it from pathogen concentration, which is very simple. If, say, I am sick, I am not, but if I am sick, then where I'm located and where's the AC, etc., then you can pick the source location and the sink's location. And if I'm talking continuously like I do, I'm ejecting droplets. And what's the probability that one of those droplets or some of those droplets will reach you with the pathogen? So that is where the concentration comes in. So that's that. So with this one, you can answer all the other questions. Now, why is it so hard? You can think about it. Why can't you, I mean, with all this machinery, why is it so hard? You can see that there's so many parameters. There are room details. There are ventilation details. ACH is a number I will keep using often. It's nothing but air changes per hour. Okay, so typically in this room, you may have about 7 ACH. So in other words, every hour, the ventilation removes 7 times this room volume, pushes it out and brings new air. So the higher the ACH, the room is extremely ventilated. Now, on the other hand, if you don't have an AC and you have all the doors closed, ACH could be just 0.3 or something like that. In other words, it takes 3-4 hours to clean up the room. Okay, so ACH is a very important thing. And of course, whether I'm talking, singing, sneezing, the mode of ejection, source details, where I'm located. So there's so many things. So how do you make a guideline that works under all conditions? So that's where the challenge is. We can do large eddy simulation, lots of things. If I know all the details, considering that one particular case is not a very difficult thing. But how do you make a science out of it so that anybody can use? Okay. So that is the key challenge in this problem. So way to make progress is that let's look at this problem. The problem is too complicated, so let's divide and conquer. Let's first look at the viral scale problem. So this has to do with how many viruses are ejected, does it live for an hour, and how many you need to inhale to get sick. These are beyond my capability, but others have looked at this problem, so we need not worry about this. The next one is puff scale problem. So this is a very important thing. When I talk or when I sneeze, you can see even millimeter sized droplets, and most of them fall. Some of them stay up in the air, and unfortunately, those are the ones you can't see because they are too small and they drift and go everywhere. So the first question is the puff scale problem. By talking, sneezing, what are the size ranges that stay airborne? That's the first question. Now, once I have that, then I can then talk about room scale problem. Okay, I have a certain number of droplets, say between 100 nanometers to 10 micron up in the air. What's the probability of it reaching that corner or that corner everywhere? That's a room scale problem. Both the problem, if we do those problems and post them and answer them in a manner that can help science-based guidelines, that's the sort of the goal. Now, optimization problem, I'm not going to say anything. If you solve these two problems, then you can put it on a package, on a software, etc. Somebody can ask what the maximum number of seating I can have in a restaurant, or airlines can use it. Lots of other people can use it, but that's an optimization problem, and I'm not going to talk about that. But those are the sequence that we had in mind. So here is the view of what really happened. So this is what we are unable to see, but this is what happens is that when this person coughed or sneezed, ejected about half a liter of fluid and a maximum velocity of 6 meters per second with 90,000 droplets. And you can see large droplets just fall. But what you see here is hot puff of air, and it still contains maybe 60, 70,000 of the droplets, which are small. And the other thing that happens is that many of those droplets quickly evaporate and they became what I will call nuclei. I will keep using the terminology nuclei, but if you want, you can use aerosol if you want, okay? Now, the same thing people have seen, this is Lydia's image. This puff can travel easily 6-7 meters. I mean, especially a loud cough or a sneeze can spread quite a bit. But of course, that's not good enough for it to reach the four corners of this auditorium. So airborne spreading is very important, okay? The few facts I want you to pay attention to are, even though the ejection was half a liter, very quickly it becomes 1 liter, 2 liters, because the puff entrains here, it gets bigger and bigger. That's first thing. Second thing, many large droplets fall out. But while they're falling, many of them evaporate also. If some of the droplets, which were ejected maybe say at 50 micron, if you left it by itself, it would have fallen within seconds. But it rapidly evaporates and becomes only 10 micron particle because most of the water is gone. And it takes less than a second for evaporation, okay? And then once they become very small, they are easy to carry by air and go all the way. So the competition between evaporation and settling is very important. If settling wins, they become foamite. I talked about how droplets fall on surface, etc. Now, when the evaporation wins and it makes the droplets very small, then it's easy to take them all over the place. So they become airborne. And the other thing is that you can clearly see this is chaotic and there's a lot of voids. So this is another view of the same thing, so I don't want to spend much time. So you can see that a lot of small droplets just stay up in the air and spread. So right as I speak, many aerosols are coming out, and that's a very natural process. Okay. Some of these points I've already mentioned, but one of the things that I want to say is that the input to this sort of like a puff scale problem is one of the very important things is the room temperature and humidity. Okay, humidity is very important is because if it is humid, like Chennai or I am from Florida, in Florida, the droplets evaporate ever slow slightly. Compared to say Delhi or Arizona, where the droplets evaporate much more rapidly. So not being evaporating fast is good because that means the droplet stays big and then it falls out. Okay, if it rapidly evaporates, it really becomes very small, very fast, and then goes out. So that's one of the important things that I will show you some results. So the question is that at the end of the thing, we need to know what remains airborne. So that's the key output of this puff scale problem. Now, I won't go into all the details. I have listed 3 recent papers. They go through all the details. I just wanted to give a talk to a broader audience. So I won't go into all the gory fluid mechanical details. So one of the theories, so we developed a theory to describe the puff because we want to be describing how many droplets stay in the air, whether it's talking, singing, every activity for every ambient condition. I want to say what remains in the air. That can be a daunting task. So we need a theory to help us come up with those numbers. So the theory is a very simple one. So you have a puff or a jet. Typically, they are associated with some virtual origin. In other words, you go backward in length and time and assume that it is ejected from a point source. So all of them can be obtained in terms of how much volume is ejected, what's the momentum of ejection, and so on and so forth. So the details are in the papers, and I will skip it. And very simple theory. We saw Newton's law, how the puff moves, what's the drag on it, the entrainment law, how the puff increases in mass, and the buoyancy is preserved. So we solved these equations and we got a very simple answer. The most interesting one is the shaded one. S is nothing but the size of the puff, how it increases as a power law, and the distance it travels is a power law. So very simple results we got. But the power laws, as you may imagine, that it gets part of the answer, it doesn't get the pre-coefficients, etc. That we have to get through simulations, and which is what we have done. So we did simulations like this. So this puff with droplets. So initially we just mainly the puff, and we monitor how what the shape of the puff. It sort of looks like a prolate spheroid. This is an American football, not the Indian. So it's more like a rugby. It's shaped like a rugby. And then we also calculate what the centroid, how far the centroid moves over time, what the maximum extent, because the maximum extent is very important, because how far the puff itself directly can go is of interest. So we calculated all these things from our simulations. So here I have plotted for several different, so since the problem is chaotic, you can have ideally exactly the same thing, but every cough is not the same. Okay, so in other words, there is slight variation. They evolve slightly differently, but the centroid roughly moves about the same. And the theory does a very good job in predicting the theory does a very good job. So basically, the theory can be used instead of the simulation in predicting how the puff moves. On the other hand, the maximum extent of the puff sort of depends whether it's chaotic, whether there is a piece of it, sort of like this kind of small structures. They self-propel themselves and they move fast. Some of them go very far, a couple of meters, and others they don't. So varying scenarios can be seen. Okay. Again, these are additional statistics. Let me skip in the interest of time. So these are sort of like exaggerated views. This is the blown up views of these droplets that are so a wide variety of droplets of ejected, and some of them propel themselves very fast. So we try to look at this chaotic nature of the droplet dynamics while they are simultaneously evaporating. So these droplets, like I said, they fall out. They have complex spiraling motion. Within the puff, they seem to be fairly well mixed and well distributed. And also I said that they evaporate rather quickly. The one thing I want to point out, again, I said that these the ejected droplets, they have mucus, leftover food particles, viruses, and what have you. Therefore, what happens is that if you eject, say, 100 micron droplet, very quickly it evaporates. And maybe even if you have only 1% non-volatile in there, and I've said that in this slide here, even if you have 1% volatile, it's surprising if you have a droplet of 100 micron and 99% evaporates and only 1% remains, it will be 22 microns. It's not small, it's pretty big. And it can contain a lot of pathogens in them. So the droplet evaporation is important and the droplet fallout is important. And that competition decides what the biggest droplet size that remains airborne. I said earlier that in dry weather, a lot of droplets a droplet nuclei will remain airborne. In wet weather or humid weather, not so many. So we should all be very happy that we are in Chennai and it's humid. So this is sort of like one summary slide. I don't want to get into great details. So this is like droplets size versus number. This yellow colored line is the initial size spectra. So this is what somebody, let's say, ejects. Now, I'm not saying this is the real one. It could be any other shape. So we just took for sort of our study this to be a Pareto. This is called a Pareto distribution. And what evaporation does is simply left shift. So because it just, every droplet reduces to say 22% of its original size. If it was 10 micron, it becomes 2.2 microns. If it is 100 microns, it becomes 22 microns. That's what evaporation does. While evaporation is happening, some of it evaporated, but larger ones are unevaporated. So, but this picture is not important because within a second or two, this is what you're going to see because the evaporation is very, very fast. And then eventually you get this kind of a spectrum and the gravity sets a cutoff, the maximum size. So the take-home message is very, very simple. Well, I will get to the take-home message in a minute. But here what I'm showing is that some of the details of the droplets, say droplet centroid location as a function of time. The dashed line, the black dashed line is the theory. Theory does a very good job. And as I said earlier, this plot goes through some details saying that the amount of virus that remains airborne in dry weather is a lot more than wet weather or humid weather. That's the main thing. So in dry weather, about 16% of the ejected viral content will remain airborne, whereas in humid weather, only 2% remain airborne. So it's a significant difference whether, so you can decide whether to keep your home or room humid or dry. Okay, so that's a choice for you to make that you might want to consult this kind of a result. Anyway, I want to move on to sort of the main take-home message summary for this puff phase so that I can talk about the room scale for another 15 minutes before I finish my talk. What droplets get ejected right out of my upper respiratory tract? That's a physiological factor. I mean, it's very hard to constrain it. Somebody's cough may be different from another person's cough and so on and so forth. But one thing for sure, if you tell me what somebody's spectrum is, it simply left shifts due to evaporation. Okay, that's a very simple fact. And that happens very fast within few seconds. Maybe in a humid weather, it may be a little more delayed. It may take maybe 20 seconds, 30 seconds, but evaporation is rather fast. The second fact that's very important is that ambient humidity determines the largest airborne nuclei. Everybody eventually fairly quickly evaporates, but the largest size remaining airborne depends on whether how efficiently gravitational settling is able to pull things out before they remain airborne. Okay, so in that sense, dry weather is not very good. Okay. So that point being made, I want to move to the second part. So we have a fairly good idea: speaking, singing, coughing, etc. What's going to remain airborne is fairly well set. Okay, so let's take that for granted and we move on. Okay, if I know what the ejection rate from a person that's going to remain airborne, what happened? So we took a very canonical room, 10 meters by 10 meters by 3.5 meters, and we put a LG four-way cassette air conditioner on top. So it has 4 jets, and then it sucks up air through the center outlet. So there are 4 outlets through which air comes out, and then it circulates and goes. This is just one ideal situation, but I'm pretty sure the answers I'm going to show, though are specific to this configuration, are generic enough, applies to many other cases as well. Okay. So what do we want in a room scale analysis? A very simple thing. I'm going to give the puff scale problem as the input. I will tell you how much airborne virus laden droplets going to be there, ejected by a person at some point in the room. I want to know what is the concentration of pathogen somewhere else. Very simple room scale problem. So let's try to see how we can do this. Now, before doing that, how have people analyzed room scale problem? Because this is a fairly complicated problem, because the sick person can be anywhere in the room. The to be infected person could be anywhere in the room. So it's a mind-boggling 6 degrees of freedom problem. How do we tackle this? And then on top of it, room size, ACH. I mean, it's a formidable problem in terms of when you think about it, to come up with a general answer to it. Okay. So one of the things people did, been done for more than 70 years, and this is the state of the art, okay? They say, well, the room is well mixed, okay? Well mixed is a very strong assumption, because it says if I talk, instantly it mixes everywhere and is instantly available to every one of you in equal proportion. And it's clear to see that that is not going to be true. Okay, but the 6 foot, all the social distancing guidelines are based on this assumption. Okay, that it's well mixed. Okay, but it turns out that it's not a bad assumption. Okay, maybe not for this bigger room, but at least for a 10 meter by 10 meter room, it's not a bad assumption. It's a pretty good assumption. But our interest was to do a little better than that, and I will tell you how we do that. But the well mixed assumption is very easy. Concentration is a constant in the entire room. Concentration changes with time because of production and loss. Okay, this is chemical engineers will understand. This is the stir tank problem. So production is the production at which I eject my droplet. This comes from the puff scale problem I showed earlier. V is the volume of the room, and lambdas are the loss coefficients, decay terms. Okay, so here there are 4 mechanisms by which the viruses disappear. One, ventilation sucks out some of the stuff, and then even the airborne ones slowly settle down, and there could be filtration somewhere in the room, or the viruses could be dead. They don't be alive for a while. So there is a rate at which they deactivate. So you take all these things. So here is a very simple answer. This is what they try. C infinity is a very simple thing. They say a sick person comes in, enters the room, and stays for a long time. Then dC by dt goes to 0. So you just have P by V, and this whole term is equal to 0. So you can calculate what is the final terminal concentration. Okay, and that depends on the production rate, and it also balanced by the these rates. So this is called the well-mixed theory, and within the well-mixed theory, you can come up with simple model for what does the ventilation do. Is ACH is air changes per hour divided by volume of the room. Settling, you look at the settling velocity of 10 micron or whatever size you want, or is the size of the nuclei divided by height of the room. So very simple estimations. So this is the well-mixed theory. So what I want to do in the next, so using this, they come up with maps like this. This particular one, I took it from Basant and Bush. So this is the cumulative exposure time. So on the y-axis, how many people can be in the room? On the x-axis is the how long you can be in the room without mask, with mask. You can have a lot of different things. The blue line, when you have natural ventilation, the ACH is low. Red line is when you have strong ventilation. For example, they say in this room, if you demand that people be 6 feet away, then there can be only 8 people who can sit in this room. And then for 8 people, they can safely be there by less than an hour and a half in this case. Okay, this is assuming they wear a mask or something like that. If they go higher, they will be subjected to, I think the risk factor in this case is 10%. They will have a risk higher than 10%. Okay, so this is how the guidelines will have to be drawn. Very simple, so that you can give it to someone that they can use to decide whether to allow 10 people or 20 people, or how long someone can stay in a room. Okay, so this is for a nursing home. This is a little bit more stringent. So you can see the safe time. There can be only 2 people in that nursing home room, and they can stay only for a couple of minutes. Okay, because here the risk factor is being set to 1%. In other words, very tight requirement. Okay, so things like that. Ultimately, this is the kind of thing people want to be able to draw. I want to talk about some visual interpretations of what happened. So this is what the Prof scale problem, the earlier simulation. So this is the near scale problem that we already solved. And here is the source of, this is a particular cough. Now, I want to show you in the next slide what happens if this guy coughs or something, and then the room scale ventilation goes on. This is in 1 minute. This is about 2 minutes. Okay. This is a ACH of about 5. I don't remember exactly. It's all over the room. Okay, and the same thing right now happening. This is one person in this part. It could be a different person in a different room, and it's spread fairly. This is a patient lying on back in the middle of the room, and then coughs or sneezes, or it could be breathing. Only thing is that in breathing, there is a continuous release and the continuous spreading and so on and so forth. So this is how it spread. This is a large area simulation of how the viral particle spreads. I mean, once you have, you can have fun. So the student got excited and said, hey, I put a mother, a child, and something else. What happens? So you can play scenarios. But the interesting thing that you see is that, well, should we do one LES for every single case? How many LES am I going to do? When am I going to solve this problem and answer? So that's an interesting question. But the problem turns out to be much simpler. Since these droplets are not changing the flow, we call it one-way coupled. Therefore, we said, why don't we do the following? Why don't we just put virus-laden particles everywhere? I mean, it's just a simulation. So we said that we populate the entire room and we gather statistics. We gather statistics of every kind, saying that the source, which is the sick person, can be anywhere, and the receiving person can anywhere. Tell me anything. I have one simulation I do, and I collect all the data. Okay, it may be an expensive simulation. I run it for 2 days, and I collect enormous amount of data, and it tells everything about that room, and I can make now graphs like I showed earlier. Okay, that's the plan, and that's what we have been doing. We also put 10 different sizes, going from 100 nanometers to 50 microns, and we watch everything. Of course, 50 micron will not spread as easily, etc. So this is what we did. And out of which, and I don't have time to go through all the details, there's a lot of details, but just to give you a general idea, is that one of our things is that first question is, how good is well mixed? If well mixed is good, why bother? Okay, they have done a great job, so keep using it. But deep in our mind, we all know that, yeah, 2 meters is not the same as 20 meters, because that's what well mixed theory says. So we say, well, really, how good is well mixed? Especially, entrenched ideas to question that it's a risky business. So we are proceeding very gingerly because the whole world is using well-mixed theory, okay? So we want to be careful. So we want to build our case. So we took 4 different scenarios. We said, okay, look, we are doing a LES. I can do an average, which is, I call it a double average. What the double average is, average over all source sick person's position and average over all receiving person's position. Okay, and that's what the well-mixed theory says. When we do that, what does the simulation say? Does it jive with the mixed well-mixed theory? The second thing is that you can average only over all sink locations is a source perspective. That's a very interesting question. You know, you can ask a question: if a sick person were to come in this room, where should that person be standing? Okay, here, here. Which location for the source will make the lowest impact on the average concentration for the room? Okay, you can turn around and you can ask this, another question. This is more interesting from our perspective. If we have to enter a room, is there a better place to sit in the room where my concentration will be minimal? Because I don't know where the sick person is. Okay, should I sit under the air conditioning vent? So these are very interesting questions. With our simulation, we can answer the question: are there special places where, if I don't know where the source is there a special sink location? Or are there bad sink locations? Okay, so there are questions like that you can ask. The final thing is that, you know, there may be specific questions one has. If you have a classroom, like the auditorium, this is a great example. You know where the source is going to be. Okay, you put the source here, you can see where the sink is, etc. So we want to sort of build, and we can see how good is well-mixed theory. Every one of these analysis we compare with our well-mixed theory, and we say how good it is. Okay. Again, I said that there's a lot of detail. I can't go through all the details, but one thing I want to say: the well-mixed theory says, I showed you plots of number of people times safe exposure time. And let's say that plot, I call that plot to be well-mixed theory. Now, what if I tell you I can multiply that by a correction factor? And that will be the new, not so well-mixed number of people times tau. So in other words, if n times tau is 10, my correction factor is 1/3. That means it's 3 times more riskier, okay, than well-mixed theory says. So in other words, what we want to do is that all the analysis I showed earlier, I want to titrate into one simple parameter, which is a correction factor. So we want to tell everybody, go use your well-mixed theory, but here is your correction factor. And that correction factor will depend on whether you say 2 meters, 4 meters, 6 meters, 8 meters. So bring the distance into the picture, and also bring ACH and other factors into picture. So we want to bring down the answer to a very simple gamma. And I will finally, in a couple of slides, I will show you some results for gamma. So the gamma, the lower the gamma, well-mixed theory is not very good. If gamma is 1, well-mixed theory is very good. If gamma is less than 1, it typically is less than 1. If it's far less than 1, then well-mixed theory is not good, etc. Okay, actually, that's not true. Gamma can be greater than 1. For example, you know, well-mixed theory is on average. If your other person is going to be 15 meters away, well-mixed theory is too constraining. You could do better than the well-mixed theory. Okay, so the gamma, I shouldn't say that it is less than 1. It could be less than 1. It could be greater than 1. Okay. Anyway, I want to just down to my last 3-4 more slides. There are a lot of details, and I won't go through all those details. What we said here is that this is basically a sick person walks in at this time t equal to 0, and what is the concentration? Normalized concentration. How does it build up? So a small droplet is the blue line, and the large droplets is the red line. Okay, the large droplets reach their asymptotic concentration. The concentration is low because most of them fall down, but it reaches very, very fast. Okay, within 200, 300 seconds, a person walks in, there the large droplets, which is, I'm talking here about 15 micron, 20 micron, 30 micron droplets, population will be set immediately. But whereas when you think of nanometer sized droplets, it takes a lot more time to reach their asymptotic value. Even after 1/3 of an hour, you can see it hasn't reached its asymptotic value. Okay. Now, these are simulation results, and the exponential beautifully fit. Therefore, the well-mixed theory is excellent because well-mixed theory predicts the function to be exponential. They do seem to follow very nicely exponential. These are double average, so these are average over all sources and sinks. And then the symbols, the cross marks are well-mixed theory, and the squares are the simulation results. Well-mixed theory is excellent in predicting this, the room average kind of. Only thing it's not able to take care of distances, but as far as room average concerned, well-mixed theory is excellent. Okay. The other thing is that we can collapse the data when we divide everything with ACS. ACS is nothing but air changes per second. So which is air changes per hour divided by 3,600. Okay. So this is just a simple scaling, seems to beautifully collapse. So I don't need to do every ventilation strength. If I do one ventilation strength, I'm able to predict the answer for every other ventilation. So this makes simulation pretty easy. Okay. So this is the source perspective that I was talking about, which is saying, are there special source locations within the room where it is better for an infected person to be located? So if you have a hospital room and you want to put a sick patient in somewhere, this question is a very relevant question. Are there special rooms, given your ventilation, where do you place that person so that the room concentration of the virus will be low? The answer is here. So it depends on size, of course, whether you're talking about 200 nanometer particle, this is 10 micron particle, this is 50 micron particle. These are horizontal contours of concentration. These are vertical contours of concentration within the room. Just to give you, because this is a 3D field, so I'm just giving you a few slices. Yeah, there are some better spots for you. So this is the PDF. So the lower values of PDF are good. That means concentration is low. The darker regions are bad region. So certainly you can see that near the wall, the concentrations of intermediate and large size droplets will be a lot. Now remember, volume goes as R cubed. Therefore, larger droplets will have a lot more viruses. So inhaling one large droplet could be lethal compared to inhaling many small droplets. So there are special rooms. But one thing is interesting is that the variance of these PDFs is plotted here, and the variance is very small. What that says is, though these colorful pictures are there, it's reasonably well mixed. There is really no better, at least in this particular room for this ventilation, there isn't an amazingly wonderful spot to put anybody, okay? So well-mixed theory seems to be reasonable even in this case. So let me move on. This is the other question, which is what is the sink location? Say, for example, you entered this room, where do you want to stand so that your chance of having virus be the lowest, and you don't know who is sick, okay? So that's because this has been averaged over all source locations. And we find that, yeah, if you stand directly under the ventilation, it's good. Now, obviously, you don't need to be a rocket scientist to predict that, but that's what the theory says, that there are spots where the concentration is low. But again, the change, the variation from the high concentration to low concentration isn't like 2 times or 3 times like that. It's like 30%, 40% variation. So even if it is 3 sigma, you don't see a whole lot of variation. Again, seems to be well-mixed theory is not perfect, but not bad. Now, what I want to show you is that, but those are all good because there is averaging involved. And that is anytime you have averaging, it sort of makes well-mixed theory look good, okay? Now we say, I don't want to do any more average because we're not living in an average world. And I'm standing here and you're standing there. The question is, am I going to get sick or not? Okay, some very specific question. So we said that, okay, there is a sick person somewhere in this room. And then I draw here one surface of 1 meter, surface 2 meters, 4 meters, and I ask a question, what will be the concentration at these surfaces, and how does it compare with the well-mixed theory? Now, this surface, this green surface is twice the concentration. This is 1 time. So you can see at a distance of 2 meters, well mixed theory can be off by about 100%. So in other words, you could have a twice the concentration. And if you get closer, you could get 4 times the concentration. So in other words, distance does matter. If you get into some specific detail, distance will get matter. So these surfaces are great because guidelines are being given in terms of 2 meters. Okay. So I want to answer, hey, is 2 meters really safe? Okay. Is well mixed theory applicable for 2 meters? So that's a fair question. And we want to answer that question. And that's the answer that's in here. So you can see the black line is 1 meter distance. Red line is 2 meters distance. This is the mean concentration normalized by room average concentration, well mixed theory concentration. So what you see is that you really need to go to 4 meters for well mixed theory to be. 4 meters is where the well mixed theory works. If you're going to be closer than 4 meters, then the concentration could be worse than or higher than what the well mixed theory predicts. Okay, so for 2 meters, you could have about 70% more exposure. This is the droplet settling velocity or droplet size. Now, as you go to larger and droplets, and I said that the larger the droplet, if you inhale, you have the volume is so large that the dosage could be lethal. So you could have a significant distance effect come in. So 2 meters isn't really, well mixed theory isn't really good. And the standard deviation, so this is the mean. So in other words, if you look at the surface, you can see, you can take on this surface, not only you have a mean concentration, say if you take the red line, it's about 1.7, but you also have a plus or minus about 0.5. So in other words, you can have some spots where you could have much enhanced concentration of pathogen. Okay. So finally, I said that the correction factor gamma. So my student just sent me this information just yesterday. This is very recent result. He sent me 1 over gamma instead of gamma. So you can see, we can come up with a very simple correction factor to the well mixed theory. Okay. I won't go into the great details. So you can say, hey, I have a restaurant and I'm going to put my tables at 2 meters and I want to use well mixed theory. And you go here and say, well, I have to use the well mixed theory with a correction factor of 1.5 to 1.6. Okay, so this is the kind of idea that we have with a very simple correction factor one can take from a much more detailed analysis. Of course, everything I showed is for one room, and you can do it for any room like this and create your own correction maps, and then you're done. So that's the kind of viewpoint I have. The last slide, I'm sorry, I really wanted to redraw these blue lines. I mean, it's a very easy thing to do, but my student never sent me that slide, so I just retained the old slide. But you get the picture that these are these curves given by Bazant and Bush, beautiful paper. Please, if you have time, read it. That's a very nice paper on social distancing. So what we are saying is that, yes, we now have a correction factor. I can draw a new blue line and a new red line, and I can make predictions of what should one do if one wants to stay safe. It's a little bit more work, but probably it's well worth it, and you get a better prediction. And that brings me to my last slide. I again want to thank all the people that you have done great work. Well mixed theory is a great baseline, and a correction factor is a very simple way. It's an approximate, but I said at the very beginning that unless it's simple, nobody will use it. So we hope that somebody will use it. I haven't said anything about optimization. The other thing is that, which is what I want to do eventually, is that even to ask people to do LES for any room, it's too much. I mean, we need much more cheaper way. Maybe we can do RANs or we can do machine learning to predict the room scale flow. So the opportunities are immense to make them. Eventually, what I want to do is that we are working on it, is build a tool where people can give their room specification, ventilation, and ACH, etc., and you predict the flow, predict the statistics, and you give the correction factor, build it up with the well mixed theory, and you can plot the social distancing guidelines, and that's where we are heading. And I want to thank you for listening to me. So that's my last slide. I don't know how long did I take.